So, welcome to Chapter 5 of College Physics Second Edition for OpenStax text for Aquinas University Physics without calculus. Today, we'll be going over further applications of Newton laws. These are friction, drag, and elasticity. They are short equations that go into the Newton's three laws of motion problems and your projectile motion problems to better describe real world questions, right? Talked about in the previous couple chapters that we're ignoring XYZ thing. This is stuff we're ignoring when it comes to, again, drag or friction, what have you. As with all my other lectures, I'm going to be going between the OpenStax created PowerPoint and the book itself. I will be referencing back to particular questions from the text, but I will not go over every single one. This is to be a resource for you, not the only way you learn this material. And if you have any questions, feel free to send me an email or leave them in the comments below. With that, let's get into it. So why are we discussing this stuff? Well, friction, drag, and elasticity are, as I said previously, the real world application to some of the problems we've been discussing at this classical physics, Newtonian physics level. They play a big enough role in solving problems that you run into that they cannot be avoided. A classic example would be medical use, right? Hip replacement surgeries happen very commonly, but it's very important that there is a very low level of friction in a hip joint replacement, for example, in order for it to function more or less similar to the original piece that it's replacing. If you replace a hip and the pieces don't move very well because there's tons of friction, I don't think the patient's going to be very happy that his hip barely moves. Friction is essentially the irregularities in a material catching each other. Something may seem smooth to you at first, but in fact, it's not smooth. And those slight Velcro-like irregularities in the real world cause the friction that we're talking about here. Friction is overcome, of course, but how much effort, how much work it takes to overcome friction. This stuff is usually followed by work in other books, but how much work it takes to overcome said friction and how much friction impedes your motion in a direction can play a big factor of things, right? Classic example, of course, is put your hand on the desk in front of you and start to push it forward. You're going to hit a point to where your hand releases from the table and starts to slide. And if you pay very close attention to the feeling of your hand, you're going to feel like your skin pull back a bit, right? And tighten up before it actually breaks. That is friction. Your hand has bumps and pieces and dips and stuff to it, as does the table. And essentially, if you do this on something smoother, it's going to take you less effort before you finally break that frictional barrier. If you do something with a higher degree of friction, it'll take more, right? Take your phone if you want, put your phone, screen side up so don't scratch it, and see how much effort it takes to move your phone, right? If you got a case, take the case off to where it's just the hard plastic, and you'll find that it probably takes less effort to move your phone because the hard plastic of your phone's actual case is smoother than, I'm going to guess, whatever protective case you have on your phone. That's how friction works. Friction, we always define as going the opposite direction of motion or opposing motion. If you're moving something one way, friction by definition moves the other way. In the same way as talked previous, gravity always pulls you down, so the normal force associated pushes up, right? Newton's third law of motion, equal and opposite forces. It's kind of what's going on here. And last part on this, by definition, nothing's friction-free because in order for it to be friction-free, you would have to not touch anything. If it's not touching anything, it still experiences a friction, but we call it something different. We'll get to that. Call it drag. A couple more picture examples of the conversation we're having. Let's go over a quick, super classic. Every time you talk about physics, you always talk about a skier going down a hill, right? Here in the text describes everything I was just talking about, kinetic versus static friction, stuff like that, and the equations associated with the friction. So the force of the friction is a combination of the force involved in the motion and what's known as the mu of friction, or the coefficient of friction. It is a defined variable for what you're dealing with, right? And these defined variables can deal with static or kinetic friction. They kind of the same equation, and they are knowns, right? Here's a big long list of the knowns. Usually the question's going to either give you this information or ask you to solve it. So you don't need to like memorize the static friction of Teflon or something. You can if you want to. I don't know. So let's go over the example of skiing. A skier with a mass of 62 kilograms is sliding down a snowy slope. Find the coefficient of kinetic friction for the skier if friction is known to be 45 newtons. So coefficient of kinetic friction is your mu value. It's asking you to determine the mu value. And it will given a diagram here to explain what's going on. So as discussed in previous chapters, any angled motion, such as this 25-degree angle, has by definition a x and a y component to that angled motion. And you use those x and y components to solve the problem at hand, which is what we're doing here. The normal force is equal to the perpendicular of the weight, perpendicular, of course, to so parallel to the surface, perpendicular to the individual. And that is given to us by the weight of the skier, the 62 kilograms, times the cosine of theta, theta being 25. So you need to go back to your previous chapters to kind of catch this stuff up, right? Yeah, we did talk about breaking down into components for X's and Y's and what have you. And this is a practical example of that. I think the picture does a pretty good job of illustrating this. The gravity is pulling the skier straight down, but the question cares about the 25-degree angle of the hill. So I need to know what gravity is doing in reference to the hill itself. And since friction is defined in part by the material and in part by the weight, right? The heavier something is, the harder it is to push. You need to know what gravity is doing to the weight perpendicular to the ski slope. So that's why that YW perpendicular is what we care about. If I was asking for how fast he's going or something like that, and I cared about his speed, then W parallel being to the ski slope would be the important question I need to have answered. So I figure out the force. What was my equation here? I figure out my newtons, right? My force given. And then I'm told the force of the friction of 45 newtons. So I rearrange my equation to solve for the coefficient mu and math it. 0.082 is the coefficient of friction. Coefficient of friction is a unitless scalar. So you just say the number, right? And what was it again? 0.06? Yeah, 0.082. So does that make sense? 0.08. Closest we get to that is like 0.1. So a slightly less friction than, say, ice on ice or shoes on ice. And that can make sense. So you've been skiing, you go pretty fast, right? They're groomed, the skis are designed to go super fast. That makes sense. Cool. And I've said this to you many, many, many times, right? The math itself is not difficult. All that was finding my equation, finding my variables, and solving for what I need. The actual math part was multiplication and division with a cosine. So let's just build out your question correctly. See here, more stuff about friction, kind of going over what I said already. The larger the surface area, the more contact you have, therefore the more friction. It's a lot easier for you to push your finger across the table as to push your entire hand across the table, that sort of thing. And this goes down to like a molecular level and the interactions of the particles and the fields of the particles creating the friction so that you know. I guess. If you get into more advanced physics, you'll see how this stuff relates at a more advanced level, especially deal with like nanomachines and stuff like that. If you get there, at this point, friction exists based on how much stuff is touching. So if you're dealing with frictional forces, but you're not touching something, you're probably dealing with air's friction. The friction that air imparts on something, because air is a fluid, right? Air has particles in it. The friction that air imparts on something is what we call drag. And it describes, right, how aerodynamic something is how much it reduces the drag on a component. This here, a bobsled race a car, maybe. I don't know what bobsleds are called, what the vehicle for bobsled is called, but they're designed to be very, very slick to reduce the effects of the air drag, allowing them to go faster, right? You test the wind chambers for this sort of thing. It's very, very lucrative field, knowing how to design something to get a little bit more potency out of every drop of fuel possible, right? That's if you look back at cars in the 1910s and 20s, all very square and box shaped, because they understand the relevance of drag back then compared to nowadays. High end vehicles like NASCAR or Indy cars especially are designed to be very, very aerodynamic and resist the force of drag as much as possible. Famously, the Olympics, what was that, 10 years ago, maybe? Yeah, a little over 10 years ago, they started allowing swimmers in the Olympics to wear special suits to reduce the friction. Essentially, those suits that the swimmers are wearing here, I think that's Michael Phelps in the center, those suits have a lower frictional contact with the water than human skin does. So the swimmers can swim faster because they have to fight water's drag and water's friction essentially less by 10%, as that says right there. This applies to lots of things we see in nature. This is why geese fly in a V, right? All this stuff plays a part, and you never quite know where in your professional world this will become of use. So understanding at least this basic concept, and essentially the same concept as friction, but the equation is slightly different because we deal with different things here. Cool. Go through, here are the equations for drag force. Again, we're dealing with multiplication here, nothing too super difficult, but knowing your variables is important. So some of the variables involved with force include a drag coefficient, which is similar again to the mu coefficient for friction, same concept. The area of whatever you're dealing with, how much is being hit by the air, right? That's why sleek cars are very thin. The density of the fluid, again, a known product if you're flying through air versus water versus syrup, I guess, and how fast you're going, velocity squared, right? I believe I actually skip here some examples of coefficients that we talked about. I believe I actually skipped the questions from here because, again, these questions are very straightforward. Figure out your knowns and unknowns, plug them in, right? Terminal velocity questions. Because I move on to elasticity. Elasticity is the last general, general and common additional thing to Newton's laws. This, of course, refers to a spring, usually, but elasticity kind of refers to everything. Everything to some varying degree is elastic, and that's what we're talking about with this diagram here. Everything bends before it breaks, and that bending is the elasticity. Not everything returns back to its original form as easily, but by definition, everything bends. A spring is the most obvious example of this. As you pull a string back, when you let go, it compresses again and oscillates back and forth, right? That's your elastic region, but you can pull a string too far and it damages, it permanently deforms or even breaks, fractures, and it won't come back. Any material has a diagram similar to the one we're looking at here that describes what it interacts with from forces. Again, commonly in these classes we use springs because they're obvious, right? I don't need to explain that a spring is elastic to you. The how elastic something is and how the elasticity is applied and affects things is defined by the physical properties of what you're dealing with. A plastic slinky behaves differently from a metal slinky. A large slinky behaves differently from a small slinky. A slinky with very thick made of very thick wire behaves differently from a slinky from very thin wire. All of these variables play into account, and this again is a repeated conversation. That's why all three of these in the same chapter, because you need to know your variables and find your equations that play, and then you can solve the problems being asked. Here we have an example of some gondolas from Japan. How fun. Again, take a look at our equations here. We got a force, a constant K, and a delta L, or amount of deformation, change in length, right? Hooke's law, very, very common, very classic approach. Compression and things like that work more or less in the same way. How much something compresses is related to a bunch of factors, including its elastic modulus, how stretchable it is, Y, cross-sectional area, original length, new length, all these things, right? This equation is different in what it cares about, but we're basically doing the same thing with each three of these. We have a coefficient for the material. We have how much it's changing or how much force is applied, and we have how big it is. Here we have Young's modulus and shear and bulk moduluses. These shear and bulk modulus refer to the different ways you can bend and contort things. Best done via examples. So let's go into one here so you can see the math be played out. Suspension cables are used to carry gondolas at ski resorts, as pictured below. Consider a suspension cable that includes an unsupported span of 3,020 meters. So between the two poles of the suspension line is 3,020 meters. Calculate the amount of stretch in the steel cable. Assume that the cable has a set diameter of 5.6 centimeters, and the maximum tension it could withstand is 3 times 10 to the 6 newtons. So how much is the cable stretching for that? Again, everything will bend, and at some point, everything will break. So a steel cable, you don't really think of a steel cable as like stretching and bending. You think of it as very rigid, but they do, and that's why we use them in these applications, because they like to stretch and bend quite a bit, actually. So we're given knowns, and we're asked a question, and we need to find an equation that explains what's going on. The question being asked is, calculate the amount of stretch. Stretch is a change in displacement or a lengthening of something, right? So we are trying to solve for a L, a change in length. We are given a distance, we're given a diameter, and we're given a max tensional force. So what does this tell us? Well, tension, again, is a force, and we can figure out the area from a diameter, right? Because the equation we care about asks for an area, A. So what is the area of a cable? Well, cables are circles, so the cross-section A is given by pi r squared. Math it out, plug and chug in our numbers, right? Because we know the force. We know the modulus, in this case, because it's a steel cable, so it can go up. And again, if it's not given to you, look it up, right? We can go and you can find the tension modulus for steel. It's like 210 times 10 to the ninth. Yep, 210 times 10 to the ninth, there at the bottom. And we plug in our numbers and solve our problems. 10 times 10 to the ninth seems like it's a gigantic number, but given that our force is 10 to the sixth, the math works itself out at the end, right? And we end with a total stretch of about 18 meters. Cool. All right. Again, these questions are not giving you math problems that you don't know how to solve. You just need to go to your equations and find your variables over and over and over again. And as said before, the way that if mechanical engineers need to care about this stuff a lot, material engineers need to care about this stuff a lot, because knowing how something will be affected gives you an understanding of what material you should use and how you should design what you're talking about. The question here, 18 meters of distortion, 18 meters of length change seems like a lot, but over a 3,000 meter spread, we're talking about less than 1% total stretch. So if that's acceptable to the parameters of what you're building, then go ahead and use steel cable. If you need something more rigid for XYZ reason, you would find something more rigid, but there's a good chance the more rigid thing is also more expensive. It's probably gonna be an alloy or something like that, right? Cool. Yep. This kind of applies to everything. All these different questions are different ways to ask about the same variables, right? Here's a bookshelf kneeling over or applying weight to a nail. We've all hung a picture up on a wall, right? You tack a nail in there, and the heavier that thing that you're hanging up on the wall, the heavier the nail, or maybe you put something behind the nail. Oh my gosh, I'm losing my words here. Anchor, there we go. Or you anchor the nail in some way so it stays, right? You don't want to hang up a giant antique mirror with just little paneling nails. The nail's gonna fall down and shatter. So 5.5 is a mathing behind this. Yep, shear deformation, as we said. And the other one I think was stress. Was it? Yeah. Keep scrolling down here. But these are just equations, right? I give you the equation, I give you what all the letters mean. When I ask you a question, correlate the numbers with the letters and plug and chug. Here we go. Calculating force required to deform. That nail does not bend under much under a load. Find the mass of a picture hanging from a steel nail, shown below, given the nail bends only 1.8 micrometers, so a teeny tiny amount, and assume the shear modulus is known to two significant figures. So if I give you this question and I ask you, find the mass that's causing this picture to happen, can you solve that problem? Well, probably, right? Let's take a look and figure out what equations we need, figure out what knowns we have and what unknowns we have, and then if we can solve it, given the information provided. So what am I asking? I'm asking for a weight. Okay, cool. Do I have an equation that has weight in it? Not necessarily, right? But I have equations that have forces in them. And I know from this image, gravity is pulling the thing down, and the equation for the force of gravity has weight in it, right? So if I solve for F, the force being pulled on there, I can dissect out the weight of the thing once I know the force that's pulling it down. What else am I given? Well, I'm given a diameter for the nail of 1.5 millimeters. I'm given a change in distance given this force, 1.8 micrometers. And it looks like I'm given a L naught, or a how far away the bend is actually happening, right? It looks to be 5 millimeters. So the bend of 1.8 micrometers happens over a spread of 5 millimeters. Cool. Given lots of information, let's see what goes where. So I do have an equation from the text that is delta x equals 1 over s times f over a times L naught. And then I can rearrange for force, because force is the thing I'm looking to solve, and then fill in the information I need. So what is S? Well, S is the shear modulus of any given. Let's see, 5.3, I think it said was here we go. S is the shear modulus, so how much something is shearing down, bending down, given a material. So we know the nail is steel, I believe, right? Yeah, the nail is steel. So I can go in my equation and find the shear modulus of steel is 80 times 10 to the 9th Newton per meter squared. And then I can know my radius of what I'm talking about to figure out my cross-sectional area, because I know the diameter is 1.5, cut that in half, times it by pi r squared. I got my cross-sectional radius of my nail. So my F equals SA over L naught times delta X. Well, I know my A, I know my S, so I just need L naught and a delta X. L naught is given by the diagram, the length of the bending, essentially, 5. And the delta X is also given by the diagram, 1.8 micrometers. Again, it's important to realize that the information I'm giving you is in different units, right? So S and A were given by meters, but S is given to you in newtons per meter squared, but the area is given to you by radius in millimeters. So we have to tack on that 10 to the negative 6. People screw this up all the time, right? And then the L naught and the X are also given in various knot meters. So you got to convert them with your times 10 to the blank, right? Plug in all those numbers to get a force of 51 newtons. And then, well, force equals mass times acceleration. So rearrange that for mass to find out that the nail is holding up a 5.2 kilogram object, picture, what have you, right? So that is shear modulus. Bulk modulus, same song and dance, but slightly different equation. We put a B instead of an S in there, right? Bulk modulus refers to something's bulk changing. The picture shown here is shrinking something given, say, compressional forces from the ocean or something like that. But at the end of the day, the equation is very similar, so I can go over one. If you would like to run through an example of bulk modulus change, go through the textbook and have a go at it, right? If you got any questions, you can, of course, shoot me a email or text, let me know. But that is, in essence, chapter 5. It's kind of a short and sweet one, 3 equations, 3 real-world examples. It is very common to be given a question in classical physics, and these are going to be parts of the overall response. So I'm going to ask, it's very possible for you to be asked a simple question, but you need to dive into all these different things to find all the variables out to solve the problem. All right. Thanks for watching. Got any questions? Shoot me an email, leave a comment, and take care.